Hello, we start now a new part of the course. In this part, we are going to study the thermodynamic modeling of our simulation. This first chapter, which is entitled Methods and Models, deals with the selection of the property model. The selection of the property model is a key action when starting a simulation because it defines the reliability of the results we are obtaining. We will start by defining the concept of property model. The property model is the first step you must do when you start a simulation in Aspen Properties, Aspen Plus, or HYSYS. A property method is a collection of both methods and models that Aspen Plus or Aspen Properties or HYSYS uses to compute thermodynamic and transport properties. Here you can find the list of the most important properties used by Aspen or HYSYS in simulations. They are divided into two groups: thermodynamic, fugacity, enthalpy, entropy, Gibbs energy and volume or density, and transport properties: viscosity, thermal conductivity, diffusion, and surface tension. To select the property model, first start the software, Aspen Properties, and next follow this list of actions. First one, select the template, in our case general with metric units. Next, specify the components, for example methanol and water. And finally, go to the methods folder and select the base method. In this case, we have chosen the activity coefficient model NRTL. The problem when selecting the property model is the high number of situations you can find. The selection of the adequate property model depends not only on the type of process you are designing, but also on the components present in your mixer and the operating conditions you are using. Here you can find 4 different typical processes. For example, a distillation column to separate methanol and acetic acid. In this case, the adequate model should use activity coefficients for strong interactions in the liquid phase and consider also association in the vapor phase because of the presence of an organic acid. These are some of the adequate property methods. In the case of fractional crystallization of two salts, we need a method able to reproduce the behavior of electrolytes. For example, ELEC and RTL. A different situation is the separation of air components by cryogenic distillation. In this case, we need an equation of a state able to represent the behavior of nonpolar compounds at high pressure, for example, Rydlich-1-Suave. And finally, a case of liquid-liquid extraction for separation of aromatic compounds. In this case, we are considering the separation of benzene, toluene, and xylene using sulfolane, a high polarity solvent, and so we need strong interactions in the liquid phase, for example, Wilson model. Before presenting the criteria we must use in the selection of the property model, we must understand how Aspen considers phase equilibrium. Phase equilibrium takes place mainly between a vapor and liquid phase, or also between two different liquid phases, although there are other possible phase equilibriums, of course. In order to achieve phase equilibrium, the fugacity of all components in both phases must be the same, vapor-liquid or liquid-liquid. Let's start by the behavior of the vapor phase. The simplest model used by Aspen is the model of ideal gas. In this case, the fugacity of components is calculated to be equal to the partial pressure. This model is suitable when we are using pressures below 10 bars. However, when pressure increases, the distance between molecules reduces because an increase in density, and the interaction between molecules starts to be important. In this case, the ideal behavior is not good to represent the behavior of the phase, and we need to introduce an equation of state. The equations of state introduce a correction coefficient, which is called fugacity coefficient. There are several available models for equations of state. Finally, a special situation corresponds to the case when association is present in the vapor phase. This is a very special case which only takes place in the case of organic acids, which form dimers, and in the case of hydrogen fluoride, with the formation of hexamers. There are special models, this one here indicated, for these cases. The liquid phase is more complicated because the density of this phase is much higher than the one of the vapor phase, and the distance between the molecules and the interaction between them is larger. For the liquid phase, the simplest model is ideal, which corresponds to Raoult's law. The fugacity of the component in the liquid phase is the molar fraction of the component multiplied by the vapor pressure of the pure component, but Because of the presence of molecular interactions, this is, the presence of molecules with a certain dipole moment, or the presence of hydrogen bonds, or the presence of functional groups, these interactions must be corrected to calculate properly the fugacity of the component. This can be done in some cases for small interactions by equations of state, using again fugacity coefficients. However, for strong interactions, most equations of states are not able to reproduce the behavior of real molecules, and we need models using the gamma-phi approach. This is the use of activity coefficients. In this case, the fugacity of the pure compound is calculated multiplying the mole fraction of the component by the activity coefficient, we need a model for this, and the fugacity of the pure compound in the liquid state. This fugacity of the pure compound is calculated by a fugacity coefficient. In this case, we need an equation of state if it's not ideal, the behavior we assume, the vapor pressure of the compound, and the Poynting factor. The Poynting factor is a small correction which is introduced when we operate at high pressures, and this factor considers the variation of the density of the liquid with pressure. The activity coefficient models considered in Aspen are Wilson, NRTL, and Uniquac. They are similar, but we must take into account that the Wilson model is not able to reproduce liquid-liquid equilibrium. All these three models require parameters from experimental values. If they are not available, we can use an alternative model, a predictive model from group contribution methods, which is the UNIFAC model. Of course, we cannot trust the values obtained by the UNIFAC model the same that those values obtained from models which use experimental parameters. In the case that in our mixture we do not have only condensable vapors, this is liquids, but also supercritical gases, for example oxygen, nitrogen, methane, we must calculate the fugacity of these components using a different model, which is Henry's law. The problem with Henry's law is that the reference state that is used is different from the one used by regular activity coefficient models, but we don't care about this because Aspen is able to handle this situation. The only question we must consider when we have this type of components is that they must be defined in a group which is the Henry components group. Then we must check that parameters are available for all these components in the major solvents. There is a special situation which corresponds to the presence of electrolytes. In Aspen there are several models available to represent this situation, but the one which is always recommended is electrolytes NRTL. Aspen has available an electrolyte wizard which will help you to define all the reactions required for modeling this situation: ions formation, salts formation, and salts precipitation. Finally, there is a group of property methods which are called flexible and predictive equations of state, the ones listed here, which are suitable for mixtures of polar and nonpolar components and supercritical gases also. And these equations can deal with high pressures and temperatures, mixtures close to the critical point, and liquid-liquid separation at high pressure. These are the most powerful set of equations available in Aspen. According to this scheme, Aspen presents the following groups of property models. The first one is ideal, which corresponds to ideal gas and liquid phases. There are also several correlations for specific components: water, natural gas, hydrocarbons or refrigerants, from NIST or from specific equations of state. Next, there are several models suitable for petroleum mixtures using correlations of fugacity of key values or specific equations of state. The next group is the one we introduced in the previous slide, flexible and predictive equations of state. Next one, liquid activity coefficients, electrolyte solutions, some models for solid processing, and finally specific equations for steam from several reference institutes.